Hello everyone. In this video, we are going to discuss mathematical models of non-Euclidean surface, tiling and tessellations. Our group consists of 6 people, which are Ting Yujing, Goh Shu-Hui, Le Lianyi, Amirul Zakwan, Muhammad Amir Shami, and Sadatul Husna. In this section, I will begin with the introduction of tiling and tessellations. A tiling or tessellations is defined as a covering of a surface using one or more geometric shapes, which are often called tiles, such that there are no gaps or overlaps between each tile. The word tessellations comes from the Latin word tessellatus, which means small square stones that made up of stone, clay, or glass, and the Greek word tessera that means four. Both meaning is pointing to the fact that the first tiling were made from square tiles as the easiest shapes to create a pattern. Tessellations were used in art and architecture alike, such as covering of walls, pavements, and ceilings of many facilities. The observing of tessellation present in nature are carried out during the Middle Ages of 19th century in order to explain its geometric structures, which resulted in numerous studies based on mathematics. While tiling of the Euclidean surface are limited to regular polygons that satisfy strict angle and edge conditions, tiling of non-Euclidean surfaces such as hyperbolic and elliptic geometries enable more complex and varied patterns due to the fundamental curvature of the surface.
In this literature review, I will summarize recent research on non-Euclidean tessellation and highlight their application across 4 main areas: architecture and design, mathematical theories, computational geometry, and material physics. In the field of architecture and design, Jawan et al. Developed a modular method for 2D tilings using 3D texture tiles. By applying parametric modeling, their method allows for flexible and aesthetic package design using repeated identical tiles. In mathematical theory, Mass and Anderson work on classifying all uniform tiling across Euclidean, spherical, and hyperbolic space. Nagaraju and Raju contribute by explaining how to construct polygonal surface through isometric edge gluing. Both studies support the theoretical foundation of tessellation structures. In computational geometry, Luz and OR introduce canonical tessellation on hyperbolic surface. This helps generate curved mesh for use in simulation and computer graphics. Bell and Putapov also create online spherical tessellation tools useful in global simulation and geodesite dome modeling. In material physics, Liu et al. Introduced a class of 2D materials, penta, M, and A, based on pentagonal tessellation. These materials show potential for advanced nanotechnology. Meanwhile, Tao, Yu Liang, and Zhu study hyperbolic lattice that supports protected corner models, which are valuable in development of photonic and quantum devices. To conclude, non-Euclidean tessellation are being applied in real-world areas beyond pure mathematics. From architecture to quantum device, they provide structural, visual, and functional advantage. These studies show how mathematical geometry contributes to innovation across science and technology.
In this part of presentation, I will discuss the methodology for validating tessellation in hyperbolic space. To classify and construct regular tessellations in any geometry, notation known as Schlafly symbol, denoted as PQ, where P represents the number of sides of each regular polygon and Q represents the number of polygons meeting at each vertex. The flowchart below illustrates the systematic method for determining whether a regular tessellation PQ exists in hyperbolic geometry given a specific value of P, where P is 5, 6, and 7. It outlines the step required to determine the range of P. The algorithm begins by taking the input P, which is the number of sides of each polygon, then going through the condition whether P is greater or equal to 3 for the existence of the tessellation. Then the output Q is calculated to determine the range of Q.
Now, I would like to explain the result. Let's begin with the case P is equal to 5. meaning that we are using the regular pentagons for the tiling. We substitute into the inequality p minus 2, q minus 2 greater than 4, where p is equal to 5. Then this implies that q is greater than 10 over 3. Since q is an integer, we can conclude that q is greater or equal to 4. It's required for a hyperbolic tessellation. If q less than or equal to 3, the angle sum at the vertex become too large and the pattern will belong to elliptic geometry. On the right, we see an example where p equal to 5 and q equal to 6, which satisfies the condition. This pattern is visualized using the Poincare disk. In Euclidean space, 6 pentagons cannot meet at a point because their angles would exist 360 degrees. But in hyperbolic space, each pentagon has a small interior angle, allowing the pattern to close up perfectly. Next is case 2, where p is equal to 6, meaning we are now using regular hexagons. By substitute the value of p into the inequality again, we might get q is greater than 3. Again, since q must be an integer, we can conclude that q is greater or equal to 4 is valid for the hyperbolic tessellations. On the right, we showed the tessellation for p is equal to 6 and q is equal to 4. This means 4 regular hexagons meet at each vertex. In Euclidean space, this would be impossible, since 4 hexagons would form 480 degrees. But in hyperbolic space, the angle shrink just enough to make this configuration possible.
This part shows how special shape called heptagon, which have 7 sides, can fit together to cover a special kind of curved space called the hyperbolic plane. In normal flat space like a piece of paper, regular heptagon can fit together perfectly without gaps or overlaps. That's because their angles are too big. But in hyperbolic geometry, space is curved, and this let heptagon bend and shrink in a way that allow them to fit neatly together. The image shows a pattern where 5 heptagons meet at every corner. This is only possible in hyperbolic space. The drawing used something called the Poincare disk model, which makes the infinite hyperbolic plane fit inside a circle. In the picture, the heptagon near the center look bigger and those near the edge look smaller, but in reality, they are all the same size in hyperbolic space. Mathematical rules help us know if a shape can tile the hyperbolic plane. Use inequality, which is p minus 2, q minus 2 bigger than 4. Here, p is the number of sides on the shape, which is 7 for heptagon, and q is how many shapes meet at each corner, which is 5 in this example. When we plug in the number in the inequality, we get 15. Since 15 is greater than 4, we know this tiling works in hyperbolic space.
In Euclidean geometry, there are only 3 types of regular polygon that can form a valid tiling on a plane, and they are the equilateral triangle, the square, and the regular hexagon. However, in this project, where we research on tiling and tessellation in non-Euclidean geometry, we found that this is not the case. In non-Euclidean geometry, there can be more than 3 types of regular polygon that tile a plane. And in our results, we study the inequality p minus 2 times q minus 2 greater than 4. What we found is, for each type of regular polygon, for example, a regular hexagon, there is only one valid tiling in Euclidean geometry, but there is a finite number of valid tilings in elliptic geometry. This is because in elliptic geometry or non-Euclidean geometry, there can be more than one type of regular hexagon, meaning a regular hexagon in non-Euclidean geometry can have different interior angles. And in hyperbolic geometry, we found that there can be infinitely many valid tilings. Hence, this shows that there are actually a lot of interesting properties in non-Euclidean geometry, and we should all study more about it.